So till last week we've been discussing about the diodes, PN junction construction and construction operation characteristics and applications of diodes. Today we will start the discussion on the bipolar junction transistors. One of the types of the transistors that we are discussing in the syllabus for under electronics. The other type we will be discussing is field effect transistor, which is in the syllabus of the third year module electronic design. So this year we will be talking about the bipolar junction transistor construction, operation, characteristics, then the applications, switching applications and amplifiers. Amplifier is a sort of a lengthy discussion because we need to talk about the DC analysis and AC analysis all. The name bipolar junction transistor, the abbreviation is BJT, which is the first three letters of the three words, BJT, bipolar junction transistor. Now the word bipolar junction implies that there are two junctions in opposite directions, bipolar, different polarities, opposite polarities, and there are two junctions, two PN junctions. So today we will be discussing about the construction and the operation of the BJT. Now if you look at the BJTs, there can be a variety of BJTs ranging from very small or very large transistors like these ones that can carry significantly large currents, maybe tens of amperes even. Now because of high current they will dissipate large amount of heat. To avoid the transistor being damaged from the heat, we need to attach this to a heat sink. So the casing itself is a metal to allow more and more heat transfer outwards from the transistor. And the design is there to fasten this, attach this to a heat sink. So you have these two keyholes, right? Underneath you will have two pins, one of the two of the three terminals, and casing is the other terminal. And a little bit smaller size like these ones and these ones. And here you can see another version. All these types are also requiring heat sinks. They can carry a couple of amperes and they will also generate a larger amount of heat. So if you don't have a heat sink, it may damage the transistor. So they are designed to be able to connect attached to a heat sink for heat conduction purposes, so to take the heat away. And then we have smaller transistors, through hole type and SMD type. Through hole type transistors, these small ones can carry, later on we will look at the data sheet and see the parameters of these transistors, small size transistors and large size transistors, few transistors. Now here you can see that this is a smaller one and it doesn't have the facility to attach it to a heat sink. And they carry maybe a half an ampere or less, and because of that they don't generate much heat and you don't need a heat sink to be there. But still, if the current exceeds the limit, it will burn, right? And the surface mount devices, they also carry significantly small currents, maybe a couple of hundreds of amperes. And some of the surface mount transistors do have the metal part underneath the transistor, so that you can have a copper pad below and let the heat be taken away. Still, the surface mount devices do carry or can carry smaller currents, maximum half an ampere, right? Not more than that. If you want large currents to be driven, you need large transistors to be used. right? So that's just a brief introduction to them. And as I already said, bipolar, so you can see that there are two types of transistors. Now when you think of NP and PN, or rather PN junctions, two PN junctions in opposite side, the center layer can be either P or N. And two PN junctions to be in opposite direction, you need to have the other layers or the opposite type layer at the ends. So NPN and PNP simply implies that the order of the layers is P, N, P and N. Here P, N and P. So in NPN transistor we have a P layer sandwiched in between two N layers. In the PNP type we have an N layer sandwiched in between two P layers. Now here you don't see any difference between the three layers. All are drawn in the same size, right? So what is this base emitter and the collector, the three terminals? Constructionally they are different. We will talk about that little later on in the discussion today. Now for analytical purposes we will be using the NPN transistor, which is usual case in most of the textbooks as well. And when it comes to PNP, everything will be in opposite direction, because you know in order to forward bias junction you need to have a reverse voltage and things like that. So we will be using the NPN transistor for the discussions, and deviations will be talked about. That is, the deviations from the NPN to the PNP will be talked when necessary. If it is not discussed, it will be exactly the opposite things, like voltage should be reverse and currents will be in the opposite direction, right, and so on and so forth for the PNP transistor. Simplified structure, as we already discussed, we have now for the NPN, as we discussed already, we use the NPN transistor for all the discussions, and in that case we have a P layer in the middle, the base, and in either side you have the collector and the emitter. They are N type layers. So when it comes to PNP transistor, the center layer is the base, again a N type, now in this case it's an N type semiconductor, and either side you have P type semiconductors. They are the emitter and the collector. Now in addition you have here the metal contacts that will be connected to the leads, and we already discussed during the discussion of the diodes, the doping concentration towards the end should be little higher in order to maintain a ohmic junction between the metal and the semiconductor, right? So that is again true in this case as well. And the junction between the emitter and the base, now here you don't see any difference between the emitter and the collector in this simplified structure. This is there just to understand how it is constructed, but fine constructional details will be discussed in the later slides. So here the junction between the emitter and the base is called the emitter base junction, or base emitter junction, or EB junction, BE junction, whatever it is, right? So it means that the junction between the two layers. Here the junction between the base and the collector either be called as the collector base junction, base collector junction, or in abbreviation CB or BC junction, right? So this shows the actual construction. Now you can see that the collector is a larger volume, much larger volume than to the other two layers, the emitter and the base, and it is deeper as well, right? It is larger in volume as well, it is deeper. You can see here the base is the thinnest layer among the three, right? And then you have the emitter, moderate size, moderate volume, moderate depth, right? Now this construction is required for the proper operation of the BJT. Not only that, doping concentration differences are also there, right? Now what is done in here is what they do in the implementation or construction of the BJT is they create an N piece, the whole N piece, and then they start doping to the P, so this whole area would become P after that process. Then again they will dope an N layer inside that P piece, right here. So after all, you will get this structure. Collector is a wider layer, largest volume, and base කරන් යනවාද කරුණා කරලා ඔය මගුලක් කරලා තියන්න ඕනේ නේද මේක ඉවරෙන්න කලින් පටන් ගන්න කලින් දන්නේ නැහැ කියන ඔයාලගේ රෙස්පොන්සිබිලිටි එක නේ ඒක කවුරු බලලා නැහැ කියනවත් වැඩක් නැහැ වැඩේ වෙන්න ඕනේ හරියට වෙලාවට ලෙක්චර් එක ඇවිල්ලා මෙතන බලන් ඉන්න ඕනේ අපි යට කිරියෙන් කෑ ගහන්න ඕනේ so this construction is required. We will talk about that a little bit later on as well, about the doping concentration differences and so on and so forth. So here you can see the volumetric differences as well as the doping density differences. Later on we will see why do we need these differences to be there, right? Emitter, or we'll start with the collector. Collector has the largest volume, as we already know, and it has the lightest doping concentration, right? Largest volume and lightest doping concentration. Base is the thinnest layer, as well it has a medium doping concentration, right? The emitter has the medium volume, moderate volume, right? And it is not very thin, it has a moderate depth as well, and it however should have the highest or heaviest doping concentration, right? Heaviest doping concentration, medium doping concentration, and lightest doping concentration, right? Now, okay, this is the doping concentration profile. You see that the emitter has the largest doping concentration, base has moderate, and the collector has the lightest doping, but you can see that towards the end of it the doping concentration rises a little bit. That is done to have that ohmic connection between the collector and the metal, otherwise it will form a non-ohmic connection. The metal semiconductor junction can be formed, right? So we don't want that to happen, because we only want two junctions to be there, that is the emitter base and the base collector PN junctions. We don't want any more junctions to be there, right, whatsoever it is. So therefore the area very close to the metal pad is heavily doped, right? But you can see otherwise it is lightly doped, right? The lightest dope is in the collector. So we will leave apart this behavior, knowing the factor that we create that only to create a metal only to avoid the metal semiconductor junction to form, right? So that is there to have a ohmic junction only, but otherwise we will consider that the doping concentration of the collector is the lightest, right? Now the BJT has three types of operation. Cutoff is like a turned off switch. Then we have the other end, the saturation is like a turned on switch or closed switch, and the active or the linear operation is in the middle, right? For amplification we need the active operation to be there. For switching purposes we will be using the cutoff and the saturation, right? The two ends. We will talk about those two later on, little bit later on. Before that we will talk about the active region and active operation, and see what if we have the cutoff and the saturation. Now for cutoff operation you can see that both the PN junctions are reverse biased or non-forward biased. For active operation we need the base emitter PN junction to be forward biased and the base collector PN junctions to be reverse biased. For saturation we want both the PN junctions to be forward biased, right? Now we will see how the other two operates. Before that we will talk about the active operation first. Now for active operation we said that we want a forward bias in the base emitter PN junction, forward bias in the base emitter PN junction, reverse bias in the base collector PN junction. So base emitter, base collector PN junctions. To create a forward bias you need a positive, this is a PNP transistor, so the base emitter has a base side has a P, so we want the positive side to be connected there, and N has the emitter has N layer, so negative side should be connecting there to forward bias that. Reverse bias is needed for the base collector PN junction, so base is connected with the negative and collector is connected with the positive. And you can see that as this is indicated, as it is indicated in here, the voltage of the base emitter is less and the external source supply for the base collector is large, right? Now let's take this out. Now here again you don't see that volumetric difference and that this is a thin layer and so on and so forth. So I am going to go out of this and let's draw the BJT in a different way. Now this is done to illustrate that you have the volumetric difference, and let's put the layers as well. Base is the thinnest layer, right? So you have the base, emitter and the collector, emitter and the base. Let's bias this as well. We want a reverse bias in the collector base PN junction and a little forward bias. Now this is a forward bias, so we know that the voltage can't be larger because the forward bias voltage of a silicon PN junction is around 0.7, so you don't need a larger forward bias to be there. Okay, so that's the biasing. Now the base emitter junction is forward biased, so you don't have any depletion layer in here. But what about the base collector PN junction? Further. Now what happens here? The differences, let's label them in red. The collector has the, okay, let's label them first in green. The volumetric, this is the largest volume. And the base is the thinnest layer. Collector, sorry, emitter has the moderate volume. Right? And what about the doping concentrations? This has the lightest, doping, and the base has moderate doping, and the emitter has heaviest doping, right? Heaviest doping, moderate doping, and lightest. Now, why do we need the emitter to be having heaviest doping? You know that this is forward biased. Larger the doping concentration, the smaller the resistance is, right? Larger the doping concentration, the more the number of charge carriers, extrinsic charge carriers or majority charge carriers are, so the higher the conduction is. So to satisfy that, we need a heavier doping in here, right? Now the other case is we have a lighter doping here. The doping concentration on this side is larger than that. Now that this is reverse biased as well, and the factor that the base is the thinnest layer, or it's a thin layer, very thin layer, what will happen? And we have a larger reverse bias voltage as well here. What will happen is the doping concentration, or rather the depletion layer, will occupy majority of the volume of the base. Now, what about the collector side? Collector has a very light doping concentration. So what should happen? Larger the doping concentration, the smaller the depletion layer penetration is. The smaller the doping concentration, the larger the depletion layer penetration is. So the collector will be occupied, or the collector, the depletion zone in the collector side will occupy a very large volume from the collector, right? And what are the, okay, now this has, now we are talking about an NPN transistor. So this is N, this is P, and this is N. So what about the charge in here? We know that the depletion layer has charges. Inside, what is the charge you have in the inside the depletion zone? Yes? What is the charge in the depletion zone? Yeah? You know about Dulles now. You know about the p-n junction. So what are the charges you have inside the N? Yes? Anyone can remember? Blank? What is the type of charges you have here? Minus? Are you sure? Why? Why minus? Yes? Now you should be logical, right? The main problem in many people is that people don't want to be logical, right? You give out an answer, whatever it is. Just something comes into your mind and you tell. Nothing logical. So what are the charges that you should have inside the depletion zone? Now you know that electrons migrate from one side to the other side and recombine with the holes to form the depletion zone. Right? So any area that has excess electrons, additional electrons will be positive or negative, and any area that doesn't have the number of electrons that supposed to be there will become positive, obviously. Right? So which side should be positive and which side should be negative now? Yes? Which side should be positive, which side should be negative? Which side should be positive? Yes? Positive in the collector. Right? Positive. Why? The electrons that were supposed to be there are moved down to the p side, that is the base. So what you should have here is a positive charge. You will have positive charges here and negative charges here. Right? Now let's assume, okay, not assume, because the base emitter p-n junction is forward biased, electrons will enter into the emitter layer and the resistance in the emitter is very small because it is heavily doped and it will easily move the electron. Anyway, it is the operation of the forward bias p-n junction and they will enter with a velocity into the base layer. Right? Now if I take this, take the base layer, or this part taken out, you will have, okay, that's the base layer. Majority of the base will be occupied by the depletion zone. So these electrons can easily go into the depletion zone. Now for the electrons, the velocity is normally distributed in general case. and you have a certain velocity which is required to go into the depletion zone, crossing the remaining base layer that is not occupied by the depletion layer, because that layer is very thin, because the base is a thin layer. Although the doping concentration is higher in that side, it is a thin layer. So as a result, most of the volume will be occupied by the depletion zone. So very large number, or there is a very high probability that an electron can move into the depletion zone. Now what happens once an electron is moved into the depletion zone? Once an electron is moved into the depletion zone, what is the force on an electron inside the depletion zone? You have negative on this side and positive on this side. What will happen to those electrons? Can they come out from the base? What happens? Why are you blank? Are you MAD? So are you following MAD or BSc engineering? Now this is the attitude that you had in the tuition classes, right? You keep your mouths open until they feed you all the rubbish into your mouths, right? That is why the government had to take a decision, a ruling to stop all tuition classes by last night for A levels. Tonight for A levels and last night for scholarship, right? Grade 5 scholarship, right? And the situation is so worse. From the kindi, the kids are sent for tuition. They don't have a childhood. They don't have time to spend with their siblings. They don't have to time. They don't have a time to spend with the parents. Right? Now just recall yourselves what happened with you. Don't let be happening with your kids. Right? Now how much did you suffer because you were pushed to go to the tuition classes? Well, tuition classes are needed. That is for needy people. If one is lagging behind, people, because that sort of a distribution is there. This sort of a normal distribution is there among people as well. There are a set of people who can absorb very well, and there are, what has happened there? There are some other people who can't absorb that well. So for the people who can't absorb that well, like maybe somewhere below this or somewhere here, you need some assistance to be given. That is okay. But what I have seen nowadays is whether your kid is needing any help or not, as a trend, people send their kids to tuitions. Not only one per subject, 2 or 3 per subject. What the hell? Right? Do you have enough time to think into yourself or study by yourself? You don't have time, right? Yes, it is a situation, right? And our stupid Sri Lankans are introducing this culture in Australia and USA as well. Whereas they don't have that culture. Right? And our stupids, Sri Lankans, I'm actually ashamed to say I'm a Sri Lankan because of this stupid attitude. Right? Why? Do you have enough time to work? Do you have enough time to think? That way we build only parrots, we create only parrots, right? Who can just read whatever is going on, that's it. No creativity, nothing. creativity is killed. Do you believe, do you accept that? Right? Creativity is nil. That is done by the tuition masters. Why am I telling that? Now tell me if I am wrong. What they do is, they give a list of maybe hundreds of questions and they teach them to you. They give you the answers as well. Don't they do that? I am talking about the math classes. Do they allow you to work out? Right? They don't, right? Tell me if I am wrong. Then maybe I am wrong, right? Then I can change my mind. At least they are doing something to you. Now, on the other hand, my teachers, what they did was, they asked us to do all the questions by ourselves. Right? They gave the just first, second examples, like from the textbook, reference book, one or two examples, and then one past paper question. That's it. That was it actually. All the rest was our work. We read the questions and we worked out those questions. So we were trained. I know the people who were going for tuition classes. I am a person who didn't go to tuition class. I went for a short period, but I realized that I am doing the same thing again, right? And wasting my time. So I stopped tuition classes. I think went for about 2 or 3 months. That was it. Right? And people who went for tuition, they came to me and asked what is the answer for the 6th question in 1995 paper? Right? I replied, say, go to hell. Right? I am not nuts to remember the question number and the answer for the years. Right? Show me the question, I'll read and understand and let you know how to do it. Let you know how to do it, but not doing it. I never sold it for them. I just gave them the way to do it, the path. And once the entire class got stuck in a question, no one in the class could do that question. So myself and one of my friends went to my PO sir. He read the question and he just said, do this and see. So he gave the starting point. That's it. That was it. We were expecting him to come to the class and explain that. No, he didn't. He just gave the starting point. This is where you should start. The rest we did. Right? So that's why I am here. And that's why I am always going with the fundamentals. Right? I have a very weak memory. You do. You also have a very weak memory. That is why you have not scored rocket high marks in the A levels. So the A level is a stupid most examination I would have ever seen. Trust me. Go back and see your papers. Try to read them and understand and answer. You won't be able to do it in the time given, 3 hours. But all you can do is, you know the model, you just follow the model. Right? Now I was in a panel setting papers for A-level art stream hardcore technology. There were hell a lot of complaints for our team. Why? We did not follow that pattern recognition culture. Right? The last year question is completely different from this year question. Right? And the mock exam question is completely different from everything else. So the people have to read it, understand, from the knowledge that they had, they have to answer. Right? That's how it is. It's not a rule set. It is not a rule set for you to follow. Right? You have to be strategical. right? You have to understand, read and understand what is asked you to do, and then solve that problem, right? Now tell me if I am wrong. If you are not willing to do that now, can come to my room and tell me what I was telling about tuition masters is wrong. If what I was telling about the tuition masters, I am talking about the maths classes, right? They give here a lot of questions, like thousands of questions, and they solve them for you, and they tell you this year this will be the model, right? Because 2 years back the model was that, last year the model was that, and they do the recognition and they expect, okay, either this or that will be the model for this year. You go to hell, right? They earn money making stupid youngsters, right? No creativity, nothing, nil, zero, right? Because all what you can do is, when you read the question, recall whether I know this model. If you know, you can answer. If not, you are dead. I can remember, I think in 2010 there was a huge discussion about the O-level maths paper, telling that the theorem that they have asked to prove is not in the syllabus. So I took the paper, because that time I was in the A-level paper setting panels, this hardcore technology. So I took the paper and I went through, because I'm also part in the examination department. That, I mean, not in the examination but I was a member of the paper setting panels. I'll tell it in Sinhala because I read the Sinhala paper, maths Sinhalese version. ත්‍රිකෝණයක කෝණ සමච්ඡේදකය සම්මුඛපාදයේ සමච්ඡේදනය කරයි නම් එම ත්‍රිකෝණය සමද්විපාද ත්‍රිකෝණයක් බව පෙන්වීම සඳහා පහත පියවර අනුගමනය කරන්න. හරක් පැටියෝ මේක කරන්න, ගොම් පැටියෝ මේක කරන්න, ඔක්කොම කියලා තියෙනවා. So the idiotic tuition masters made a big shout saying that theorem is not in the syllabus. ඒ ප්‍රමේය මොකද්ද විෂය නිර්දේශයේ නැහැ. Whereas it is not a theorem to be proven, it is a problem to be solved. And they have asked, like to cattle, you do this, you prove that is equal to this, and do that all. Why they were shouting? Because they have trained their tuition kids to stick to the model. That question has never appeared in past papers, and they have never trained their stupid pupils to face such a question. So they lose their business, right? Whereas for me, well, if I was setting that question, I would have got rid of the word prameya, right? සමද්විපාද ත්‍රිකෝණයක් ඒ ප්‍රමේය සාධනය කිරීම සඳහා කියලා දාන්න නැතුව, හරි? සමද්විපාද ත්‍රිකෝණයක් බව පෙන්වීම සඳහා කිව්වා නම් කාටවත් කෑ ගහන්න බෑ. හරි? ප්‍රමේය කියන වචනයක්වත් නැහැ. හරිද? හැබැයි කවුරු හරි හදපු කෙනා ඒ වැඩේ කරලත් නැහැ. Right? So get rid of that mindset. Read the question. Be logical. Right? Be logical. Now in here, which direction should the force be, or what would happen to an electron that is inside the base layer? You have negative charges in the base and positive charges in the collector. What would happen? What would happen? The electrons will be pushed, right? The electrons will be pushed towards the collector. So there is the electric field or force on an electron from the base to the collector, and what will happen is the electron will be accelerated through that electric field and gain a very high kinetic energy, very high velocity at this point, so that although it is you have a field here or distance here to be traveled, the electrons gain enough energy to do that, right? It is accelerated towards this field, electric field. That is why you need a very light doping concentration in here. Lighter the doping concentration, the more the volume that will be occupied by the depletion layer. So acceleration process will take place throughout a larger distance in the collector, and you have only a smaller distance to be traveled, right? It is like you go at 100 kilometers per hour in the highway and put to neutral by the exit way. You have enough energy to travel till the toll gate, right? Whether it is a manual gear or auto gear, without throttling you can reach the toll gate without any problem. So it is like this. You know that there is friction, right? The tire friction is, road friction, air friction, everything is there, right? Overriding all that, because you had a velocity of 100, you can easily reach the toll gate. So this, you can't go 1 kilometer with that energy, can you? No. But that few hundreds of meters possible. So you have a very short distance to travel. The energy is sufficient enough to travel that distance. So as a result, what will happen is there will be a huge electron flow injection, electron injection from the emitter to the collector, right? There is a huge electron injection from the emitter to the collector. Now what will happen? What about the base? Some electrons come out from the base, yes, of course, because there is this small number of electrons that didn't have energy to go into the depletion zone of the base layer. They will walk out. They will come out from the base, right, making the base current. Now the result is that with a very small collector current, this is IB, small, you will have a large I'll say ECE, that is the collector to emitter current. This is a large value, right? That's a large value, very large value, right? So that's the operation of the BJT. Now for that, okay, let's look at what if we didn't have the required doping concentrations, right? Now what if the base had a lower doping concentration than the collector? Then the collector depletion layer penetration will be less and the base depletion layer penetration will be high. So we will not have the enough length for acceleration, right? You know this, you have solved the questions in the applied section, applied mathematics. If you give a constant acceleration, right, you keep on increasing. So longer the distance that it travels at the constant acceleration, the larger the volume velocity that it will gain, right? Same thing would happen because it's a constant electric field that it has. So constant force, F is equal to ma, so acceleration is constant, right? See, well, physics stuff comes here, right? They are electrons, it's okay, right? But this is substance, right? Nature, right? Different things at different levels, right? So don't restrict your knowledge that you have gained in one place to learn something else, right? That may be meaningful. Now you know that F is equal to ma, right? So certain force is there. Electric field means force. So constant force, constant velocity, constant acceleration therefore, and the velocity increases. So larger the distance that it will travel, the larger the ultimate velocity would be, right? And the other hand, if base has a lower doping concentration here, the depletion layer penetration would be 100% easily, right? To avoid that, we have a larger doping concentration in the base than the collector, right? So, and again, now in here about this place, the depletion layer penetration X, depletion layer penetration X on the P side, or X of the base at base collector PN junction is much less smaller than the X of C at BC junction. That is because the doping concentration, N of the collector is much smaller than that of the base, right? And that is smaller than that of the emitter. So emitter has very large doping concentration, base has intermediate, collector has the smallest doping concentration. Right, so that's the operation. Although this does not look like meaningful, the other diagram has a meaning. Its volumetric difference is shown, acceleration field is shown, and so on and so forth. And I have drawn that diagram to have a sufficient to illustrate that the volume in the emitter is not very large, right? It is smaller compared to the volume of the collector. Collector has a larger volume, so all these is illustrated. All those are illustrated inside in this diagram, right? What next? Then the voltages and currents. So with respect to the ground of the circuit, the voltage of the collector is VC, voltage of the emitter is VE, voltage of the base is VB. Then we know the voltage of point A with respect to B is VAB. So here this voltage with the arrow on this side, that is actually the voltage of the collector with respect to emitter, is VCE, and VCB or VCB and VBE, right? The symbol arrow shows the emitter, and the current, forward current in the base emitter is shown by the direction of the arrow in the emitter. So in that case, for the PNP, the base emitter to be forward biased, emitter should be positive, base should be negative, and the forward current will go from the emitter to the base. So that is why you have this inward arrow, right? Arrow indicates the emitter, direction of the arrow indicates the forward bias current in the base emitter PN junction. Now if it was for a PNP transistor, emitter will be P, base will be N, collector will be P. Then this voltage has to be reversed in order to forward bias the P-N junction between the base and the emitter. And to reverse bias this, you need a positive here and positive there. So everything will be opposite, and instead of electrons we will be talking about the holes, right? Not electrons, then it will be hole propagation. Now we will look at the cutoff and saturation applications or operations. In cutoff both will be reverse biased. So let's assume that the base is disconnected, right? Base is disconnected, right? Cutoff operation, let's assume that you have something like this, right? You have the transistor, and you just keep it open, right? When you keep it open, what will happen here? You have a reverse bias PN junction and a forward bias PN junction from the voltage between the emitter to the collector. You have a reverse bias, so there won't be any current going through it. In the active operation, current goes because the base emitter PN junction is now forward biased. But in the cutoff, base emitter PN junction is not forward biased. Let's assume that you disconnect the base terminal from the supplies, so base is not biased, right? Then you have a reverse bias junction to be overcome, which will not happen until you reach the breakdown voltage, the Zener breakdown, these are moderated dopes, so they will have the avalanche breakdown. Until the avalanche breakdown happens in the base collector PN junction, there won't be anything happening, right? So we can assume that it is like a off switch. There won't be any current going through this, only the leakage current will go through. Saturation current, reverse saturation current, which is negligibly small, right? And the situation here is even worse than a diode, because in the diode you only have the reverse bias PN junction, but here we have a reverse and forward, so drop voltage is divided between those two as well, right? So you need a even larger voltage to break down the reverse bias PN junction, so the current will be negligibly small, right? So that is cutoff. What about saturation? Saturation, we want a positive voltage to be rather forward biasing voltage in both. Let's assume that you have around 0.7 volts here and around 0.3 volts here, or 0. Let's say 5, right? 0.5 volts here, forward biasing but not forward conduction. Now what is the voltage that you have here then? 7 minus 5, it is 0.2 volts. Still you have a forward voltage, and what will be the current through this path? Because now this is forward biased, the depletion layer here is reduced to a great extent, right? The reverse bias voltage, or when the depletion zone here is reduced to a great extent, right? So that you can have conduction happening, right? So that is saturation. As you can see here, the voltage here is around 0.2, which means it's like a closed switch. Well, for these switches, the voltage drop is almost zero because they are copper, right? These switches, everything we made them in metals, copper or maybe aluminium, some other metal, still the voltage drop is almost zero. There may be millivolt drop there, but we can assume that as zero. Here it's around 0.2, 0.3 volts, but considering like switching applications, for around 10 volts, 0.2 drop is negligible, right? So this can be considered as on. This is saturation. This is as on and this is as off, right? So these two are for switching operation, off and on operation. For amplification operation, we go for the active mode of operation for the BJT. Now the collector current. We know that the base current, or the relationship between the base current and the emitter current, this is a forward bias PN junction, right? For a forward bias diode, or for a diode, we know that the characteristic equation is ID equals IS e to the power Vt, or rather Vd over Vt minus 1. This can be approximated to ID equals Is e to the power Vd over Vt for a forward bias, because 1 becomes negligibly small, right? Now when it comes to a PN junction, or the base emitter PN junction, similar characteristic has to be there. So IB will be equal to some Is, it is not necessarily be the same thing, into e to the power VBE over Vt. And they have found that IC is proportional to IB and IC is equal to beta IB for the BJT. With that, with all these, we can write IC equals to beta Is e to the power VBE over Vt. Now let us label this as some other Is, let's say Is dash e to the power VBE over Vt, right? That is what that relationship is, right? Is is in fact the reverse saturation current of a PN junction into beta. Now you can see the equation or the relationship for the Is. It depends on the cross-sectional area, the doping concentrations, then the diffusion velocities of the base, and so on and so forth, right? Effective width of the base, everything, right? Right. So this is that. So in this case they have taken IB as capital Is over beta VBE e to the power VBE over Vt, right? I started in a different point of view, they have started in a different point of view. Now the beta is known as the common emitter current gain. We will talk about what is this common emitter later on. In general terms, this is also referred to as the current gain of the BJT. right? IC over IB. So IC is equal to beta IB, and it's in the range of typically in the range of 50 to 200, right? Okay, let's look at this. Now let's take this transistor. We have IB, IE and IC. If we apply KCL, to the BJT, we can write IE is equal to IB plus IC, right? Now IC is beta IB, so we will write IB is equal to IC over beta plus IC. So this is 1 plus beta over beta IC. So we can write IC is equal to beta over 1 plus beta IE, right? IC is equal to beta over 1 plus beta I. Now let's label this as let alpha be equal to beta over 1 plus beta. So IC is equal to alpha IE, right? Now this is one relationship, the relationship between alpha and beta. And there is another relationship. I mean, there are two equations that we already discussed. One is IC is equal to beta IB and IC is equal to alpha IE. Two relationships. Both are having IC as the main value. IC is equal to beta IB, IC is equal to alpha IE, right? Later on we will realize, you will realize why you need this equation in place. Let's look at that later on, right? Write things in right places. Now what about this alpha? Let's assume if beta equals to 100, what about alpha? What is the value of alpha? Calculate. You can't do it from your brain, right? How much is it? See the point? How much? Do the calculation and see. .99. If beta equals to 50, how much? 0.98. Now from here we can see that beta alpha is equal to beta over 1 plus beta. So definitely 1 plus beta is larger than beta. So therefore alpha is less than 1. That is for sure. But here you can see that because beta is a larger value compared to 1, from this we can see that alpha is close to 1 as well. Right? Alpha is very close to 1. Less than 1, always less than 1. But it is very close to, it is touching 1. Right? It is very close to 1. Now because of that, here you can see IC is equal to alpha IE, and alpha is very close to 1, meaning that IC approximately equal to IE. So you may do that approximation when you don't want to play with the beta, right? But I would recommend you to use do that. I mean, not to do the approximation when beta is available. Whenever possible, don't go with the approximation, but you can do that approximation as well for convenience. There is no harm, right? 99%, 98%, and the transistors would have even larger beta values. Let's take a few transistor examples and see. So that is this equation, right? This relationship. Now, where are my data sheets? I don't see them here. Let's take some data sheets and right, so you have this 828, (2AC 828). The collector base voltage. Now here VCBO is VCB when the third terminal, not mentioned terminal, that is emitter, is open. No connections there. No voltage is given to that. So that is the meaning of V, whatever it is. If you have the third letter as O, the non-mentioned terminal is left open. So here, now this is a very general, I mean, very widely used common general purpose transistor, 2SC828, right? You might have known it as C828, right? The 2S part is usually not pronounced, right? Very common as C828, and the other transistor is D400. Now this is a transistor that I love very much because you merely can burn it. You can't actually burn it by doing almost everything, right? That is that much robust. Unless otherwise you exceed the current by a large value, the transistor will be safe, not very sensitive to static charges and things like that, right? Whereas D400 is not that effective, though it can carry a large current. We'll see, look at the data sheet of that as well. It is not that robust. So the voltages, where we have two versions like 30 and 45, is the collector base voltage, and the collector emitter voltage maximum 25 and 45 for the 828 and 828A, and the emitter base maximum voltage is 7. Maximum current, pulse current is 100 milliamperes. this is pulse current, and the static current is 50 milliampere. So it can carry only a little amount of current, just 50 amperes, enough to drive an LED array or something like that, right? For simple small scale switching purposes, and emitter collector base is the order of the pins. When you look from this side, this is emitter, base, and the collector. So yeah, and the power consumption, maximum power consumption is, the power rating is 400 milliwatts, and the maximum junction temperature is 150. That does mean if it is heated up beyond 150 degrees, it will burn, right? So that is 828, and D400 was there somewhere here. Where is that? D400, that has again 25 volts as the collector base and collector emitter voltages, reverse bias voltages, and then it can carry 1 ampere of current. Pulse current is 2 amperes, so much larger compared to the previous one. It was 50 milliamperes in 2SC828, but in here it's 1 ampere and 2 amperes pulse current. The current power dissipation maximum, that is the rated power dissipation, is 900 milliwatts. Again, the junction temperature is 150, so if you exceed the 150, it will burn itself. And here you have a set of data data values. You can read what all these are, and you can see this is HFE, right? That is, for the moment, consider that as the beta, right? This is another term for beta, HFE. So some of the data sheets they will mention that as beta, some of data sheets they will mention as, this parameter will be mentioned as HFE, right? That is the forward current gain or current gain of the common emitter mode, that is IC over IB, right? And now you can see BC107, 108, 109, you will be using these transistors very often for amplification purposes. Maximum power dissipation is 300 watts for all. Maximum collector current is 100 milliamperes for all, that is the the static current. Pulse current would be almost twice of that, and the maximum voltage 45, 21, 20, and beta values are also shown here. It's a range actually, because beta depends on the temperature, beta depends on other parameters as well, right? So 110 to 450, 110 to 800, 200 to 800. We will see for calculation what is the value that you have to take in later stages. This is under certain condition. IC is equal to some value when VC is equal to some value. All these are given there, right? So likewise you can see different numbers here. So if you want to find out the details about the transistor, you need to I think 82 is also given in here, right? So if you want to find the details of a transistor, you need to pick up the data sheet or the data book. This is pages. This is actually pages from a data book, right? So you take one and find out the values. Now collect emitter voltage. If you exceed that voltage, the transistor will break down, right? The transistor will go to the, particularly the collector base PN junction, the reverse bias PN junction will go to avalanche breakdown if you exceed that maximum collector emitter voltage. In this case it is 50 volts or 25 volts in 828, right? In the case of BC 109, 107 it is 40 volts, and 45 volts, I think, 45 volts, but for 108 and 109 it is 20 volts. So you should be very careful not to exceed that. Here is another data sheet of PC 107, 108. So all these values are consistent. So as I said, 300 milliamperes is the collector current, and pulse current is 200 milliamperes, 300 milliwatts, and so on and so forth. I think that's it for today. So let's wind up the class at this point for today, and next week. Now be familiar with what we have discussed in here, the operation of the BJT. So next week we will be talking about the characteristics of the BJT. The characteristics is completely because of this construction, right? So therefore, without knowing about the construction, without being familiar about the construction and the operation, it is difficult to understand the characteristics, right? Because characteristics are linked with the construction and the operation and therefore be familiar with what we have discussed today before you come to the lecture next week, right? So we shall stop at this point for today, and we will continue the discussion next week.